We will speak about the curvature-homogeneous matrix in dimension 3.
Thanks, Swan. Thanks all of you for inviting me, for coming to the talk. It's a pleasure to be back in Stony Brook once again, and seeing so many friends and getting to know new ones. The subject of my talk has to do really with a system of PDE that has turned out to have lots of interesting properties and phenomena, and in fact finally winds up. There's fortunately I can see Claude is here. It's maybe Claude will appreciate this particularly. And in fact it turns out that there are twistorial solutions to these nonlinear PDE that turn up in kind of a very unexpected way. And what I thought I'd do, since this is a colloquium talk, is say a little bit about what the motivating problem was, what the background is, and historically what the sort of interesting questions were, and talk a little bit about what the new results are, and this connection with twistor theory in particular that I think is very beautiful. And so I'm going to be talking about curvature-homogeneous 3 manifolds. And so, of course, what do I mean by that? If you and maybe it'll be easier to explain a little bit by starting with 2 manifolds. If you remember that if you have a surface, a Riemannian surface, one of the major discoveries for a surface endowed with a Riemannian metric by Gauss, in fact, was that the G determines a function, G, which is it's a quadratic form on the tangent bundle, quad form, positive definite. It determines the so-called the Gauss curvature of G, which is a function on M, and has the property that any isometry of M, that is a map of M to itself that preserves the metric, even locally, has to actually fix the Gauss curvature function. And as a consequence, the only way that the metric could be actually homogeneous is if K is constant. And so if Mg locally homogeneous implies K is constant. And the interesting thing that Gauss had already observed is that in fact the converse is true. That is that if the Gauss curvature is constant, then the metric is in fact locally homogeneous. And so in fact there's one model for every value of K, and this can be any constant. And one thing that I forgot to say and should have said is that K depends on 2 derivatives of G. That is, if you know the metric up to its 2-jet, you can figure out what K is. And basically, up to isometry, up to diffeomorphism, there's no other invariant that is functional invariant other than K. Now, the 2-dimensional case is very simple, but it describes it can be used as sort of a jumping off point for understanding all the higher dimensional cases, as Riemann himself understood that for n bigger than 2, it's not as simple as a single function, and but you can see what sort of all the second order invariants are simply by basically mimicking what happens in 2 dimensions. That is, if you have n-dimensional Riemannian manifold and you fix a point and fix not just the point, but a 2-plane, passing through that point. E is a two-plane, Gaussian two-plane in the tangent space at P. That, of course, if you have a two-plane passing through P, you can, for example, look at the space of geodesics tangent to that two-plane, and that will give you a surface. And that surface has its own Riemannian metric, and therefore it has the Gauss curvature at that point. And so there's a way to attach to each, I'll call this the sectional curvature, a way to attach to of the metric G to the two planes a function that gives the sectional curvature, that is the curvature of the sort of the flattest possible surface passing through P with a given two-dimensional tangent space at each point, the sectional curvature. And although Riemann didn't quite phrase it this way, it turns out that this has all of the second-order information about the metric, just the same way that the Gauss curvature has all the second-order information about the metric at each point. That is, if you know what this function is at a given point, in a neighborhood, if you know what it is restricted to, say, the planes passing through a single point, then you essentially know the metric up to second order, up to diffeomorphism near that point. And if this is a constant function, which is the generalization of so it could be constant if sigma g is constant, then again you have the same result. This was actually known to Riemann, that if sigma g is constant, that implies that mg is locally homogeneous. And yes, and the interesting question though is what happens if it's not, is whether or not that characterizes local homogeneity, and that turns out not to be the case. So converse isn't so. Converse doesn't.
Riemannian or constant from point.
Constant on the whole. If it's constant on the whole, on all tangent planes, then that does imply that it's locally homogeneous. But a metric can be locally homogeneous without the sigma g being constant. And in fact, the best that can happen, the best that you could obviously fix would be something like this. That is that if it were locally homogeneous, then what you'd sort of expect is that for any 2 points, what would certainly be true is that for any 2 points, there'd have to be an isomorphism of the tangent spaces. An isomorphism of the tangent spaces that would induce the same sectional curvature, right? Sectional curvature function for some isometry that's what local homogeneity would imply, right? And in fact, this is what is usually referred to as being curvature homogeneous. That is, it's homogeneous up to second order. At any 2 points, you can't distinguish the metric by looking at things just up to their second derivatives, up to diffeomorphism. So I'll call this curvature homogeneity. And in fact, obviously, if it actually is homogeneous, if the metric is locally homogeneous, then it will be curvature homogeneous. But the converse in dimension 3 and higher is not true. That's is a little bit surprising, actually. Let me talk specifically in the n equals 3 case for the moment. See, the nice thing about the three-dimensional case is that, of course, two planes are essentially the same as lines, because in 2 dimensions, in 3 dimensions, once you know the two plane, to know the two planes is the same as knowing the orthogonal vector. And in dimension 3, we can actually recover all the information of the sectional curvature by simply doing by taking what appears to be part of it, that is, averaging the two planes that pass through a given line. In dimension 3, the sectional curvature is equivalent to what's known as the Ricci curvature. Where the way you get the Ricci curvature, if you take say one particular vector, call that E1, and take an orthonormal basis, E2 and E3, if you define the Ricci curvature of E1 to be simply the sectional curvature of E1 wedge E2 plus sectional curvature of E1 wedge E3, it's easy to see that this is invariant under the choice of orthonormal frame. And this then extends. It turns out that, so I've defined it only for a unit vector, but if you now make it, it turns out to be the restriction to the unit sphere of a quadratic form. Then Ricci G is the restriction to this unit sphere bundle of a quadratic form, Ricci, which I'll still call Ricci G, on the tangent bundle, quadratic form, and then it turns out that all the information that you would get from up to isometry comparing these things is just given by the eigenvalues of Ricci. So all the second order information, is in the eigenvalues. It's a quadratic form on G. We already have another quadratic form, so we can take the eigenvalues, which I'll take as R1 less than or equal to R2 less than or equal to R3. They're continuous, but not necessarily smooth. The symmetric functions of the eigenvalues, as usual, are the smooth objects. But to be curvature homogeneous is equivalent to saying that these are constant. Constant if and only if G is curvature homogeneous. And what you'd like to do is get some understanding of what the possibilities are for curvature homogeneous things. And of course, the first thing to check is what do the homogeneous things look like? Bianchi, back in the 19th century, already classified all the homogeneous 3 manifolds. Homogeneous Riemannian 3 manifolds. And if you sort of look in this R1, R2, R3 coordinate frame, R1, R2, R3, and we put in this set of inequalities, basically you get a wedge of possible, let's see, my drawing is not so great, R1 greater than or equal to R2, that half plane intersected with the half plane R2 less than or equal to R3. That's a plane like this. ignoring the coordinates, it's a kind of a wedge. I'll draw it this way a little better. You see, it's the intersection of two half spaces. I'll think of this as R1 equals R2 equals R3. This is R1 equals R2. This is R2 equals R3. And this, the inside of the wedge is the stuff where R1 is greater than R2 is greater than R3. Well, it turns out this wedge is where these things will take values, and there's a couple of things to observe. One of them is that results out of what Bianchi got. If R1 equals R2 equals R3, this is the famous case where the sectional curvature is actually constant, and these are homogeneous. These are the if they're positive, it's a sphere or a quotient of a sphere. If it's negative, it's a quotient of hyperbolic space. If it's zero, of course, it's flat. But the interesting thing here is that it turns out that not all points of W are realized. Are realized by homogeneous metrics. That is, there are certain inequalities. There are inequalities that have to be satisfied among the constant eigenvalues, other than just this. That's one. And the second is that I'm not going to say exactly what these inequalities are. It's a little bit tricky, in fact, because the set of things that can be realized is neither open nor closed. You have to worry a little bit about various inequalities, and I don't want to get hung up on that. The other kind of curious thing is that it's not true that any two homogeneous metrics with the same values of R1, R2, R3 are isometric. So there are in fact, there's an open set in W for which there are two, and there's never more than two, or two non-isometric homogeneous metrics with same R1, R2, R3. So even knowing the metric up to second order, and even knowing that it's homogeneous, is not enough to tell you which metric it is. You actually.
Okay.
Was this yes. Bianchi? Yeah. Right. Yeah. If you just, so the way Bianchi did it, it's a little complicated. Of course, since they're homogeneous, we now know that they're quotients of Lie groups, and so you can just go through the list of things. If the symmetry group is 6-dimensional, it has to have constant sectional curvature. There's nothing with a 5-dimensional symmetry group. There's one parameter families with a 4-dimensional symmetry group, and then there's a whole bunch that have a 3-dimensional symmetry group. And you just go through in the map from Riemannian, say, Lie groups to R1, R2, R3 is not injective. It's 2-to-1 in some places. In other places, it doesn't hit anything at all. Kind of a little bit surprising, actually, that you can't see things just from second order. By the way, I should mention before I go on that this business of how can you tell when something actually is homogeneous. And how far do you have to differentiate before you can tell something is homogeneous? This was a question raised by Singer in the 1960s, and he has a famous paper in 1960 where he proves that for each integer n, there's a maximum number of derivatives you have to take before if it's homogeneous, you'll be able to tell that it's homogeneous by taking that many derivatives. That is, you look at the curvature tensor and all its covariant derivatives up to some order d of n, where n is the dimension, and if they satisfy all the right equations, then it's actually homogeneous. right? That dn, Singer's argument shows that that's dn grows quadratically. It grows roughly like n squared. That's an upper bound. And there's no known case where you actually go up to n squared. Usually you can tell much, much earlier than that. But the exact number of derivatives you have to take for, say, non-manifolds to determine whether or not it's homogeneous is not actually known. Right? But it's more than 4. Right. So it's probably worth giving an example just to show you that there's something non-trivial to talk about here. Let me just mention, like the simplest example of something that's curvature homogeneous but is not actually homogeneous is in X UV space. Consider the metric G is P of X and U dx squared plus du plus v dx squared plus dv minus u dx squared, where P satisfies P sub uu plus Cp is 0. That linear differential equation, as essentially it's an ordinary differential equation with a parameter x. Then you can compute that Ricci G is actually C times this guy, P xu dx squared plus du plus v dx squared. So that means that the eigenvalues are R1, R2, R3, well, it depends on whether C is positive or negative if you're going to get them in that right order, but there's C, C, and 0. So this metric is easily seen to be, and P is positive, I should say, so it's actually non-degenerate. P is positive. It's easy to show that this metric is actually homogeneous, is not homogeneous, but it's curvature homogeneous because the eigenvalues of Ricci are CC and 0. And while there's no complete solution if C is less than, if C is greater than or equal to 0, there's no complete solution except the homogeneous guy. But for P negative, there are lots of for C negative, there are lots of global solutions to this equation that say positive, and with the right initial conditions, you can easily make it complete. So there are lots of so there's in fact, you can see what if you let P of X and U be, say if C is minus 1, if you let P of X and U be say P naught of X cos U plus P1 of X sinh U, and P naught is bigger than absolute P1, that's always positive for all values of U, and if this integral P naught minus absolute P1 dx over R is infinity, then it's complete. So that's a basic example of the kind of thing we're talking about that's curvature homogeneous but not homogeneous. In fact, it's the covariant derivative of its curvature tensor is not 0, and in fact, depending on what P is, it actually varies. It has non-zero norm, the covariant derivative. So there are such examples. You can write some of them down explicitly, but it's natural to ask, what kind of equation is it on a metric? That is, what's the nature of the equation that specifies that the sectional curvatures, that the eigenvalues be constant? Well, because these things depend on two derivatives of the metric, and you're making three eigenvalues be constant, it's three second-order equations on the metric. But the question is, what kind of equation is it? Is it elliptic? Is it hyperbolic? Is it, what can we say about the space of solutions? Depends on the sign, it turns out. Although it doesn't. The sign of what is the interesting question. Actually, it's going to turn out that, in a certain sense, what really matters is whether they're equal or not. If they're all distinct, it turns out it doesn't matter what their signs are, as we'll see. That's maybe a little bit of a surprise. But when two of the, well, obviously, if all three of them are equal, we know what the solutions are. It's just the homogeneous, it's the constant sectional curvature guys. So there's not much to say there. But when two,
same Ricci tensor as a surface times a line, but the line doesn't split up in this case.
That's right. Yep. This is not a product metric, by the way. Right. Right. At all.
It'd be easier example in that form, but it's significantly.
Yeah, that's right. Yeah, I mean, certainly you could take a product metric, but if that was curvature homogeneous, it would be homogeneous. Yeah. Right.
Is the topology also always of that nature?
The topology of the solution. In this particular case, if the eigenvalues are C, C, and 0, then the simply connected cover is always contractible. Yes. Right. But you can get more complicated topologies with constant. For example, there are, if you take any left invariant metric on the three-sphere, for example, think of the three-sphere as a Lie group. Any left invariant metric is homogeneous, and therefore it's curvature homogeneous. And so you can get actually three-sphere topology, and you can get an open set in the space of R1, R2, R3 by looking at the left invariant metrics on the three-sphere. So yeah, you can get non-trivial topology in the solutions. Right. Okay. Yeah. But just locally, the nature of the equation is kind of interesting, and I want to say a little bit about what the solutions can look like. The first you would think that this problem had been looked at a long time ago, but the first place that I was actually able to find any substantial result on the non-homogeneous case is relatively recent, in 1998. Kowalski and Prüfer. They showed that any R1 less than R2 less than R3 occurs as a curvature homogeneous metric. And their proof was a little well, elaborate, perhaps, is one word for it. So what did they do? I mean, as I said, it's a system of PDE that has it, but it's a degenerate system of PDE because it's invariant under the diffeomorphism group. And so what they did was they chose some normalizing coordinates and wrote out the PDE essentially, and then checked that they could construct a convergent power series that satisfied the equations. And they basically used the sort of these standard Malgrange arguments that say if you have some formally integrable system, you carry it far enough out, you get the initial conditions right, you can prove that there is a convergence. There is a sequence of jets that convert that has convergent Taylor series that satisfies the equations.
Grammatically relevant?
No, they're not, in fact. But their argument their argument definitely depended on real analyticity. I mean, they assumed that they were looking for a real analytic metric. They assumed there was a real analytic metric, and then they made these coordinate normalizations and whatnot, and were able to produce a solution.
And so the solutions they produced were real analytic.
Yes, absolutely right.
Non-real analytic.
Yeah, that's right. And when I say produce, I mean sort of produce. They showed they existed. They could not actually write down a solution, right? But they showed they existed, and in the neighborhood of a point, basically. They didn't get any estimates on the radius of convergence or anything like that. But they did, in particular, these regions that don't actually show up in the homogeneous case, their solutions had to be non-homogeneous. But you can actually get a somewhat more precise theorem, and let me. What I wanted to the first result I wanted to talk about is that somewhat more precise result. But to do that, let me introduce a piece of terminology. I'll say that if M3G is curvature homogeneous, a coframing omega 1, omega 2, omega 3 is diagonal if G is omega 1 squared plus omega 2 squared plus omega 3 squared, and Ricci G is R1 omega 1 squared plus R2 omega 2 squared plus R3 omega 3 squared. And in the case that you have strict inequality, there's always locally anyway, and if you pass to a simply connected cover, and at most, in fact, eightfold cover, you can get a smooth diagonal coframing by on a suitable cover of M3 if it's curvature homogeneous. And what you can ask is, how do you express the condition on a given coframing that it comes from, that it's the diagonal coframing of a curvature homogeneous metric, right? And this has three parts. One part shouldn't be too surprising, is that if omega 1, omega 2, omega 3 is a diagonal coframing of G curvature homogeneous, then omega satisfies a system SR that depends on this R is R1, R2, R3, satisfies a system SR consisting of three first-order equations and six second-order equations. These are PDE, actually. I should have just used PDE. What do I mean by three first-order PDE? For example, it turns out that you get something like this, like R1 minus R3 d omega 1 wedge omega 2 plus R2 minus R3 d omega 2 wedge omega 1 is identically 0. That's an identity if it's a diagonal coframing for a curvature homogeneous metric. And similarly, if you commute 1, 2, 3, you get three equations of that kind, right? And those are all first-order equations because they only involve one derivative of omega. So So there are 3 first-order equations, but those 3 first-order equations are not enough. There's actually 6 second-order equations that you have to also adjoin in order to guarantee that when you compute the Levi-Civita connection of the omegas, that its Ricci curvature actually looks like this, right? So that's not too surprising. This is sort of what was a little bit surprising was that there actually even are 3 first-order equations, because you sort of think of it's 3 second-order equations on the metric, but of course the omegas themselves that diagonalize, they depend on 2 derivatives of the metric, and it's not exactly clear how you can recover. You have to do a little bit of work and conversely, I'm not saying it precisely, but I think you know what I mean. That is, if you have a coframing that satisfies this system of 3 first-order PDE and 6 second-order PDE, then it is the diagonal coframing of a curvature-homogeneous metric. Right? So now this looks more or less okay in the sense that a coframing, of course, is a choice of 3 forms that are linearly independent, and that's in local coordinates. That's 9 functions, and this is now 9 equations for those 9 functions, right? It's just that it's mixed order. There's 3 first-order equations and 6 second-order equations. That's one slightly weird thing about it. The other, of course, is that it's invariant under the diffeomorphism group. So it can't be completely non-degenerate. You cannot expect to put it into say like Cauchy-Kovalevsky form and solve the initial value problem, because it's invariant under the diffeomorphism group. Knowing it along a surface is not going to tell you what the metric is, right? Or at least that's what it looks like at first glance. But if you just treat this as a system of degenerate PDE by the method of by either Cartan-Kaler or Spencer or Malgrange, their standard treatment for overdetermined nonlinear systems of PDE that works even in the degenerate case, you can check that this system is involutive. The system SR is involutive with characters S1, S2, S3 is 6, 3, and 0. I don't have time to go into the definition of what involutive is at the moment, but let me just say it means that this system has the property that all of its compatibility conditions are derived simply by differentiating the equations, and it never doubles back on you and gives you lower order equations. That is, if you differentiate the 3 equations, you don't get any more second order equations than the stuff that was there in the 6. And if you differentiate the 6, you don't no combination of them drops down and gives you like first order equations or anything like that. So it's formally integrable and in fact involutive, meaning that any k-jet of a solution can be extended to a k+1 jet smoothly. The sequence of jet bundle projections is a sequence of smooth submersions all the time. This is again sort of a calculation. That's straightforward. This is a calculation, and for those of you who are trying to sort of keep track of the characteristic variety here, it turns out that because this S2 is 3, what it says is that in the projectivized tangent bundle, the characteristic variety is a curve of degree 3. So when you projectivize the tangent bundle, the cotangent bundle, PT star is of course P2, and the characteristic variety is a curve of degree 3. In fact, it turns out to be 3 lines in general position. If the equations had been elliptic for example, this would have had to have been a curve with no real points, but in fact it's 3 real lines in general position. If the equation were going to be as hyperbolic, as smoothly hyperbolic as you wanted it to be, it would have had to have been a smooth curve of degree 3, but it's not a smooth curve of degree 3. It has 3 singular points. So, and that'll come up again in just a minute. The third point is maybe it gives a little bit more. Maybe it explains a little bit more about what this involutive means. Is the following: is if sigma is a surface, and let's say eta, which is eta 1, eta 2, eta 3, are 3 one-forms on sigma, are 3 one-forms on sigma, such that eta 1, eta I wedge eta j is not 0 for I not equal to j, that are real analytic, in some coordinates, then there is a 3 manifold M containing sigma and a coframing omega, omega 1, omega 2, omega 3, such that omega satisfies SR, and the pullback of omega I to sigma is eta I. Moreover, M is germ unique. Sorry, M omega is germ unique up to diffeomorphism. Up to diffeo. Yeah.
So you're generally just viewing their pullbacks on sigma when you say
yes, that's right.
Linear independent.
They're pairwise linearly independent on the surface, and so what this is saying is that if you take a surface with 3 one-forms that are pairwise linearly independent, then then that surface essentially has a unique embedding into a curvature-homogeneous 3 manifold, so that the etas are the pullback to that surface of the diagonal coframing of a curvature-homogeneous metric on the.
Arbitrary, R1, R2, R3?
Yes, distinct. That's important. I should have said somewhere up here that I'm always assuming they're distinct. They're fixed. Cartan-Kähler. Cartan-Kähler, yeah, right. So which is essentially, I mean, you have to deal with the fact that the system of equations you're solving is of different orders, and they have compatibility conditions, etc. So you have to. So just Cauchy doesn't work, but Cartan-Kähler works, right? And if you're worried a little bit about the count, it seems a little strange when I said the solutions depend on 3 functions of 2 variables up to diffeomorphism. What's going on here? I mean, a triple of 3 forms on a surface, of course, depends on 6 functions, but you have 2 functions worth of diffeomorphisms on the surface, so you subtract, you get 4. And you might think, well, that counts off because I'm taking 4 arbitrary functions. But the difference is that, of course, M doesn't have a canonical surface sitting in it. We're choosing a surface inside M as well, and that's also choosing one function of 2 variables locally as a graph. So that's where the extra function comes from. So for example, I mean, well, you can imagine there's lots of lots of local constructions you can do that show, and it shows that you can include a fairly large surface sitting in there. and you get convergence. It's just that you may not get convergence a long way off the surface, because M is not guaranteed to be complete. Right? M is just guaranteed to exist and be unique up to diffeomorphism. Right. So that's sort of a sample of what the analysis of the differential equations go. Very likely, in fact, it's almost certainly true that that you don't need the real analyticity assumption here.
Well, I mean, you get a formal solution. Without that assumption,
You get a formal solution, right?
Convergence, right?
Right. Yes. But you need something to get the estimates to get convergence.
So it could accidentally converge for other reasons.
It could accidentally converge for other reasons. And there's there are sort of smooth versions of the Cartan-Taylor theorem, right? Unfortunately, this doesn't fit into any of those. It doesn't. You can't. There's nothing that I know of off the shelf. But we do know. There's various tricks and ideas for proving and sort of generalizing, because the characteristic variety is essentially symmetric hyperbolic, right? It's essentially 3 lines in general position. If you take a point inside the triangle, every line passes through 3 points. It's just you don't have distinct points. You have these singularities. And you might think, well, that causes trouble, but remember, for example, when Yang and de Turk were proving that every smooth 3-manifold can be locally, there's coordinates in which the metric can be diagonalized. They ran across exactly this kind of system like this, where the characteristic variety was 3 lines in general position, but they were able to prove that it was symmetric hyperbolic once it's appropriately, in appropriate coordinates, and so they got smooth existence. It's possible that there's a smooth existence theorem here, but I've not yet been able to find it. I think it's highly likely that there are, in fact, non-real analytic. I mean, that there's lots of smooth solutions that are not real analytic, no matter what the R's are, as long as they're distinct. Now, I have only about 10 minutes left. I wanted to say something about this is kind of leaving a glaring question about what happens in case 2 of the R's are equal. And here's an example where 2 of the R's are equal, and you clearly don't have real analyticity, because these functions could be anything. But there is something we can say in the 2-dimensional case. In the multiple eigenvalue case. In fact, the multiple eigenvalue case is a little bit easier to deal with than the in terms of writing down a PDE system, because you have more information. I guess it was 1996 that Kowalski and Sekizawa. Kowalski and Sekizawa, they showed that, proved that existence when R is R1, R1, R2, R2 not equal to R1. And they found examples in all these cases, even in the cases that don't, for which there's no homogeneous example, these curvature-homogeneous examples, and they did it by, in this case, it turns out you can simplify the analysis. Actually, I'm going to get confused if I call that 2. I mean, R2 is R1, right? But I'm not going to assume that R3 is bigger than R1 or not. But here's the interesting thing. It turns out that what matters when they're equal, it turns out that what matters is whether R3 is positive or not whether it's larger than or less than R1, but whether R3 is positive or not. And they proved existence in this case. And in fact, the equations are parabolic If R3 is 0, they're hyperbolic. If R3 is positive, is negative, and elliptic if R3 is positive. And so, in particular, it turns out that if R3 is positive, if you have two equal eigenvalues and that guy's positive, then these metrics are always real analytic. It turns out. Whereas you can write down examples where R3 is negative, where it's not real analytic. Again, their existence was purely local. There was no, and their method of doing it, there was no way to actually construct, to try to construct complete examples. But just last year, Schmidt and Wolfson actually constructed a bunch of complete examples in this case. And I wanted to tell you what they were before 2015. And Wolfson. They showed that on SL2R there is a family with R3 negative curvature-homogeneous family with R3 negative and R1 equals R2. Depending on one arbitrary function, on an arbitrary function of one variable. And they are all complete. As far as I know, they're this was the first known complete example, a complete example in that family that was not homogeneous. Of course, there are complete homogeneous examples, but an inhomogeneous example. And let's see, I'll just say it really quickly what they did. If you look at SL2R, SL2R, 2R, contains the parabolic subgroup, the upper triangular matrices. And if you take the left invariant form G inverse dg and write it this way, 1/2 gamma 3 minus 1/2 gamma 3 gamma 1 plus gamma 2, and you look at the projection onto SL2 R mod P, which is, as you know, it's a copy of RP1. If you choose a smooth function, f is C infinity on this guy, RP1, and you pull it back by this projection, then if you just take, I shouldn't have used G here, but if you just take the metric pi star f gamma 1 squared plus gamma 2 squared plus gamma 3 squared, it turns out that for any function whatsoever that's positive here, any positive smooth function on RP1, pull it back up to here, construct this metric. This metric has R1 equals R2, R3 negative. In fact, R3 is minus 1. I think it's R1, R2, R3 is 1, 1, minus 1. And of course, these things aren't real analytic. Right? But this is not the general solution. Unlike the solution I just erased, which turns out basically to be the general solution in the case that R3 is 0, of the non homogeneous ones. This depends on only one arbitrary function. You can prove using the Cartan-Taylor machinery that the general solution in this case depends on two functions of one variable, and this is sort of half the solutions in some sense, or in infinite codimension, I guess. Depends on how you want to count. But it does show, and these are, and as long as f is positive, this is always complete. So there's lots of such things. I wanted to finish by just mentioning a solution in the elliptic case that, I promised it would have something to do with twistor theory, and it turns out that while you can't solve the thing that matters in the R3 positive case, well, in all these cases, the thing that really matters is the ratio of R1 to R3. That's obviously by scaling, you're reduced to just trying to solve it for each possible ratio. It turns out that there are special ratios that have special that actually the nonlinear equations can be turned into Cauchy-Riemann equations. It's a theorem if R1 make sure I get this right. Oh yeah, it's R1 over R3 is 1/3. The metrics, the curvature-homogeneous metrics.
Relative to each other?
It's not, as far as I can tell. It's the same 1/3, but as you'll see, it's a completely different thing. Yeah, completely different thing, as far as I know. Right. The curvature-homogeneous metrics with R1, R2, R3, and R3 positive. These guys. Then these correspond to holomorphic curves in CP2. In CP2. And because the construction is really beautiful, and I have a minute left, let me describe what the solution is. Here's what the picture is. Look at, of course, CP2 is the quotient of SU3. It's SU3 mod a maximal subgroup of U2, and if you take any holomorphic curve, C in CP2, you can almost construct a lift into SU3 up to a maximal torus. The picture being that, of course, here you have CP2, you have the point, you have the tangent plane, and you have the Hermitian normal, and that gives you a splitting of C3 into 3 lines. And so you can actually, if you think of it like this, C sitting in CP2, SU3, and the picture, what I want to do is look at the 2 torus bundle, which is the pre-image. This is pi inverse of C. Call that B. This is a holomorphic curve. It has dimension 4. It has dimension 2. The 2 torus here gives you this guy has dimension 4, which is too big for our purposes. But if you look at the left invariant form, G inverse dG on this B4, well, because I've adapted, if you think of this as E0, E1, E2, because I've adapted E1 to be the tangent to E0, you get zeros in these slots. You have I'll call it I theta 0, I theta 1, I theta 2, where theta 0 plus theta 1 plus theta 2 is 0. You have, I'll call this omega eta minus omega bar minus eta bar. This is like the first fundamental form, second fundamental form of the curve. And look at, again, I used a G there. I shouldn't have done that. So this is the left invariant form pulled back to B. Right? If you look at this guy, 1/4 omega plus eta bar circle omega bar plus eta plus 1/4 theta 0 minus theta 2 squared. That's a quadratic form on B, but it has a kernel, namely if you look at the circle, which is given by
The circle you're using is just a symmetric product, wouldn't you?
yeah, the circle is the S1 is this. It's
Not that circle, I mean the symbol of up.
oh yeah, that's a symmetric product, right? So this is a real quadratic form on B, right? So if you look at this guy, that sits inside the maximal torus. And therefore, since B is a maximal torus bundle over C, I can take the quotient. If I take M is B divided by this quotient S1, that's a 3-manifold. And it's easy to check that G actually drops to M3. And lo and behold, this metric is curvature homogeneous with satisfying this condition. And conversely, every curvature homogeneous metric satisfying this ratio, R1 over R3 is 1/3, arises in this way for some holomorphic curve in CP2.
So these are things that have one killing field? There's a vertical killing field?
Well, there's no killing field on this guy. This guy has no symmetry, right? There's no isometry group on this guy. Right. I mean, obviously there's a symmetry group on B4, but we're going to divide out by it. Right, because this is invariant under this action of this circle. So in fact, this gives the general solution of the curvature homogeneous of the curvature homogeneous guys with R3 positive and R1 over R3 is 1/3. Actually normalized, I think R3 is actually 6 in this normalization, but it shows that you can sometimes you can solve these equations in terms of holomorphic data. It's kind of a surprise in a way. I mean, there's because if the ratio is not 1/3, there is if the ratio is for nearly none of the ratios does it turn out that there is an actual solution in terms of Cauchy-Riemann equations. It turns out you can always, for any ratio, you can always interpret the solutions as pseudo-holomorphic curves in an almost complex 4-manifold. Turns out you can always do that. But that almost complex 4-manifold, you can't actually integrate its equations to reduce it to Cauchy-Riemann equations except in this ratio. But this ratio, it works.
To be smoothly embedded is that?
Actually, I want it to be smoothly embedded, yes. Right. Although you can extend as long as the dual curve doesn't have a singularity at the same place that the curve has a singularity.
So as you described, it's a local construction, but you could take, for example, an algebraic curve, and then you would get something.
Yes. Yes. Right. Yeah.
Were you saying that the ratio of 1/3 is what gives the integrability condition for almost?
The almost complex structure itself is never integrable, but there is a way to prolong and project to another guy that is integrable. In this case, that the ratio is 1/3. That's what happens. Yeah.
Something interesting happen to the 3-manifold when the curve, say, becomes nodal or something like that?
If the curve is nodal, both it and its dual curve are nodal, then you get a singular. I mean, the metric exists, but the manifold has a singularity. Yeah. Yeah, you definitely do get things that have non-removable singularities this way. Right. Yeah. Right. But that's this was kind of the surprise for me in this story, because you don't normally expect these nonlinear equations to be explicitly solvable, but once in a while you get lucky. Right. And I think it's a beautiful solution. Somehow or another connected with classical metric algebraic geometry. Anyway, I'm way over time, so thanks.
Thanks for the beautiful lecture.
Are there any other questions?
So in this construction of Schmidt and Wolfson, you get solutions which are certainly not real analytic in given coordinates. Do they actually check that if you look at them in harmonic coordinates, then they're still not?
Oh yeah, they're not real analytic. I mean, you can, for example, if you take f to be constant, this is actually homogeneous, and so of course it's real. But now you can make f be non-constant on a bounded open set, and on some particular open set, and that definitely wiggles it away. It's not, it's not real analytic. Right. Yeah.
You also said something about contact curves.
Oh yes. There, I skipped that because I didn't have time. But it turns out that when R3, this 1/3 actually persists even when R3 is negative. But there, instead of getting SU3 as the integrator, it's SU21, and instead of having a holomorphic curve in CP2. That sort of the nice homogeneous space. It turns out that SU21 has sort of two projections to, SU21 is the CR diffeomorphisms of the ball. SU21 is the CR diffeomorphisms of the ball. So it acts on the ball, and it acts as a 2-point homogeneous space. And it turns out that if you take a pair of contact curves in that ball, that are in general position, that's the replacement for a holomorphic curve in CP2. And it turns out if you take that pair of contact curves in general position and basically do this same kind of thing, you lift up to some torus bundle and then quotient by a circle, you get things with R3 negative that have where this ratio is still 1/3, but the R3 is negative. And there you get solutions that depend on two arbitrary functions of one variable, because a contact curve in a 3-manifold depends on one arbitrary function of one variable. And that's the full generality. That actually gives the full solution in that case. Right. Yeah. Right.
Okay, let's thank.
Okay.